Expressing solution concentration. We can describe the concentration of a solution using qualitative words like dilute or concentrated. And these are just relative terms. Dilute means relatively small quantities of solute compared to the amount of solvent, and concentrated means large quantities of solute compared to the amount of solvent. And then there are a lot of quantitative measures. So here's a table from your textbook showing a bunch of them. We've already learned about molarity, so we'll just review that very briefly. And then there's these other ones, molality, mole fraction, mole percent. These are actually very similar to each other. And then parts by mass. These are very similar to each other. And parts by volume. So they're slightly different, but it all relates the amount of solute to the amount of solution or solvent. The reason there are so many different units here is because they're useful in different situations. So molarity, we looked at this in chapter 4. It's the amount of solute in moles divided by the volume of the whole solution in liters. Molarity is slightly temperature dependent because when you heat a liquid, it expands. And so at a higher temperature, the volume is larger, the molarity is smaller. And so when you're dealing with temperature changes, molarity is not the best unit to use, but it's the most common one used in chemistry. Molality, this is not a typo, it's an L, not an R. So molarity, molality, unfortunately very similar words. Molality is not temperature dependent. Here we're looking at amount of solute in moles divided by the mass of the solvent. So this is unusual. A lot of them are quantity of solution. This is quantity of solvent, measured in kilograms. The reason for kilograms is that if you're dealing with an aqueous solution, 1 liter of water would weigh 1 kilogram. And so it's going to give you similar sizes of numbers. So important, kilogram of solvent. This is independent of temperature because the mass of the solvent doesn't change with temperature. This is abbreviated with lowercase m. It's italicized. And you got to be really careful with that because it can look like meter pretty easily. So lowercase m is molality, capital M is molarity. I didn't make this stuff up. Okay, parts by mass and parts by volume. Same idea for volume and mass. Mass is mass of solute divided by mass of solution times a multiplication factor. So if you're doing percent is the part, the mass of the solute, divided by the mass of the whole thing, times 100. That's percent. Percent means per 100, so you multiply by 100. So 14%, come on, pointer. 14% by mass means 14 grams of solute per 100 grams of solution. Well, sometimes percent is too large of a unit. So we can talk about parts per million. It's abbreviated ppm. Mass of solute divided by mass of solution times a million. Parts per billion, ppb. Mass of solute divided by mass of solution times a billion. So these are all the same idea as percent, where you have the part of the thing that you're interested in divided by the whole thing times a factor. So you could do parts per trillion, then you'd multiply by a trillion. So if you have 15 parts per billion by mass, that tells you that the units used to measure the part and the whole would be mass units. They just need to be the same unit. You could do it in pounds if you wanted to. 15 parts per billion means 15 grams of solute divided by a billion grams of solution. Any questions? If we're doing parts by volume, same pattern, but we're looking at the volume of the solute divided by the volume of the solution. So 22% ethanol by volume is 22 milliliters of ethanol per 100 milliliters of solution. Parts by volume and parts by mass may be slightly different if the substances have densities that are significantly different than 1. You can also do a mass volume, which your book doesn't mention, and that would be the mass of solute divided by the volume of solution. Okay, problem. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. So there's lots of problems like these. The math is not that hard. It's just multiplying and dividing. But it's the units. So if you're good with the units, you can figure these out. And if you're not good with units yet, it's not too late to become good with units. So we're asked to find the mass of sucrose. So we'll treat this as a dimensional analysis problem and say, well, we're trying to find grams of C12, H22, O11. Contained in, so we've got some numbers here. Let's write these down. We've got 355 milliliters of soda. Soda. The 12 ounces there is just kind of for reference, right? A 12-ounce can, like this one I've got here, it says in parentheses there 355 milliliters. If you're ever stuck for conversion factors, sometimes you can get them off of the food that you're eating. They're not as precise, but they work. So 355 milliliters. The 12 ounces, we're not going to use that. And then it says 11.5% sucrose by mass. So percent is parts per 100. Right? So this is something per 100 somethings. It's percent sucrose, so this means 11.5 grams of sucrose per 100 grams of solution. Here we're calling the solution soda, per 100 grams of soda. And then we're also given a density, 1.04. I'm going to write this as a vertical fraction, grams per milliliter. That's the density of what? The soda, right? Grams of soda per milliliter of soda. So these are the numbers given to us. We've identified what we're trying to find. Now we need to figure out which of these is our starting point, and sometimes that's tricky. If you start off with the wrong one, you can go in crazy circles. Look at the units. This is milliliters. This is grams per 100 grams, grams per milliliter. Both of these could be conversion factors. 355 milliliters of soda is not a conversion factor. So that's probably what we're going to start with. So from milliliters of soda, and we're trying to get to grams of sucrose. We're going to look at what we've got available to us. Well, here we have a density, right, for the soda. We have a volume. We can use the density to calculate how many grams of soda. And then we're probably going to need to use this as well. This relates grams of sucrose to grams of soda, right?
Is that like a mole ratio?
It's a little bit like a mole ratio. It's a relationship between quantities, yeah, but it is distinct from a mole ratio. So from grams of soda, using this relationship, then I could go directly to grams of sucrose, right? So I'm just going to, that's just one long arrow. So 355 milliliters of soda. I know it seems tedious, but if you write out all the units, it's so much easier. So I'm going from milliliters of soda to grams of soda. I have two arrows. I'm going to have two conversion factors. And then I'm going to go to grams of C12, H22O11. Because those are the units I've got in my path. And then I need the previous unit to go in the denominator, so I want milliliters of soda down there. So those cancel out. And grams of soda down here, and those cancel out. So this 11%, 11.5 grams of sucrose per 100 grams of soda. So that's this last term, 11.5 grams of sucrose per 100 grams of soda. And the one in the middle is the density, 1.04 grams of soda per 1 milliliter of soda. So we got all the units to work out, and then we just multiply and divide. 355 times 1.04 times 11.5 divided by 100. 42.458, 42.5. I'm looking at sig figs. I've got 3 here, 3 here, 3 here. Does a can of soda have exactly 355 milliliters of soda? No. It's close, right? It's not exact because it's measured. Any questions? Another pair of related units, mole fraction and mole percent. So mole fraction is chi solute. It's a Greek letter. That gives us concentration as moles of solute per total moles. So the amount of solute in moles divided by the total amount of moles, both solute and solvent. So it could also be written out this way: moles of solute divided by moles of solute plus moles of solvent. And so this is thinking more about particles. What fraction of the particles are solute? Mole percent, you just take the mole fraction and multiply by 100. Okay, so this one's fun. Solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. Well, let's just start at the top. Molarity equals what? Moles per liter. So we've got moles of the sugar per liter of solution. So we need the moles of sucrose. They didn't give us moles of sucrose. They gave us grams. So we have to convert the grams to moles. So we've got 50.4 grams. We're going to multiply by moles, divided by grams. So we're going to have to calculate a molar mass. 12 times 12.01 plus 22 times 1.008 plus 11 times 16. 342 0.3 grams per mole. So let's do the math here. 50 divided by 342, 0.146. 3 sig figs, but I want to carry 2 extras. 07 moles. So I'm going to put that in the numerator. 0.14607 moles of sucrose divided by the volume in liters. Well, we've got the volume in milliliters, right? So is that going to be 355,000 liters or 0.355 liters? 0.355. Not milliliters, liters. If you have trouble and find that you get that conversion backwards a lot, think about a 2-liter bottle of soda and think about that little 10 mil graduated cylinder. You can envision how big 1 milliliter is, right? Small. Yes? Yeah, I lost the 0.4. Thank you. I've got 50 divided by. So thank you for catching that. 50.4 divided by, messed it up. 342. Yeah, so it's 14723. So 0.14723 divided by 0.355. And I'm going to just include 3 sig figs here. Well, I'm going to do this. 41473. The unit is capital M. And for 3 sig figs, it's 0.415. Capital M. Remember that capital M does not mean moles. Capital M is moles per liter. The abbreviation for moles is MOL. Lowercase m is meter, or if it's italicized, it's molality. Okay, let's look at mole fraction. What does mole fraction mean? It's moles of solute divided by total number of moles, right? So moles of sucrose divided by the moles of the whole solution. Well, there's 2 things here. There's water and there's sucrose. So we've got the moles of sucrose plus moles of water. And that's the mole fraction. Well, we already calculated moles of sucrose, so that's nice. 0.14723. And so we're going to have 0.14723 moles plus we need the moles of water. Well, 1 mole would be 18 grams. We have the mass in kilograms. So 0.332 kilograms of water is 332 grams of water. And then if we multiply by 1 mole over 18.02 grams, we can get the moles. .423 grams. So it coincidentally, sort of, ends up being similar to the molar mass of the water. So then this is 18.423 grams of water. Sorry, not grams. Yeah. I put the wrong unit on here. Moles of water. So you have to be careful on the calculator that you tell it exactly what you want to do, because it will do exactly what you say, not what you mean. So I'm getting 0.00793. $79282. What are the units on that? There's no units, right? They cancel out. And before I just blindly stick that on there. What would happen? What happens with our significant figures here? In the numerator, I've got 3. In the denominator, when I add these together, I'm going to end up with 1 decimal place. But that's still going to end up with 3 sig figs. So the mole fraction is 0.00793. Any questions? Which one would be really easy to do next? Mole percent. We just did the mole fraction. The mole percent is the mole fraction times 100. So this equals our mole fraction, 0.00793 times 100%. So that gives us 0.793%. That's percent in terms of moles. Now let's back up and do molality. Molality is what? Moles per kilogram of solvent, right? So we want moles of sugar per kilogram of water. Not the whole thing, just the water. Well, we have this information. We've got moles, 0.14723 moles. And kilograms of water is 0.332 kilograms. 0.014723 divided by 0.332. 0.044346. 0.0443, and that is lowercase italicized m. And we would read that molal. So this would be 0.415 molar, and this is 0.0443 molal. And the last one on here, percent by mass. So this would be grams of solute divided by grams of solution times 100%. So we've got 50.4 grams of sucrose. What's the mass of the solution? We were given the mass of the solute and the solvent. The solution will have the same mass as those added together. So we've got the mass of the sugar plus the mass of the water. We want it in grams instead of kilograms here. So 332 grams times 100%. So 50.4 divided by the quantity, 50.4 plus 332 times 100. 13.179, 13.2% by mass. Those numbers are all pretty different from each other, aren't they? The unit that you use depends on what you're interested in. So they're appropriate in different situations. Any questions? So we can calculate units that way. We can also take one concentration and convert it into another concentration. So here's what is the molarity of a 10.5% by mass glucose solution. And we're given the density is 1.03 grams per milliliter. So there's different ways to solve a problem like this. I'm going to start with the 10.5%. So 10.5% by mass means 10.5 grams of glucose. This is glucose instead of sucrose. Whoops. Come back to me. Oh, fine, whatever. I'll just start over. Hadn't gotten very far. 10.5 grams of glucose per 100 grams of the solution. That's what 11.5% by mass means. The molarity is moles of glucose per liter of solution. So there's two main approaches here. One is the maybe more elegant way, but might not make sense to a lot of students. You can take this and convert the grams of glucose and the grams of solution, and you can just keep it as one fraction and go across. That'll work. The other thing you can do is say, well, I've got this. I'm going to do these separately. I'm going to take 10.5 grams of glucose. I'm going to convert it to moles. And then I'm going to take 100 grams of the solution and convert it to liters. And then I'm going to plug them into my my molarity equation and just divide them. So let's look at how that would work out. So 10.5 grams of glucose. I want to convert that to moles of glucose. So I need the molar mass of glucose. 6 times 12.01 plus 12 times 1.008 plus 6 times 16. 180.2 grams per mole. So 10.5 divided by 180.2, 0.05, 8268 moles of glucose. And then I've got 100 grams of solution, and I need to convert that to liters. I'm going to need the density. The density, grams on the bottom, milliliters on the top, is 1.03 grams per milliliter. And then I can convert milliliters to liters. So that'll be 0.970 87 liters of solution. This 100 grams is considered exact. The sig figs come in the 10.5. But my density here of 1.03 limits this result to 3 sig figs. And so then I take my moles and divide by volume. .058268 divided by 0.097087, 0.600 moles per liter. Any questions? These problems are a lot easier when you get to the point where you can write things down clearly with the units.